work on this with you. Your next lesson in this unit on absolute dating. Your teaching point, this is a code that's for me right now just to get through this lesson, but I'll give you a student-centered one on your classroom page. I'll be able to connect the specific radioactive isotopes from the ESRT to date fossils and the rock record. Launch. Do you think understanding radioactive decay has any importance or use for humans beyond just the pursuit of knowledge? If yes, explain. If no, explain. All right, you can pause it here. You can think about an answer. And you can hit play once you are done. All right, with respect to radioactive decay, this has always intrigued scientists because they want to know how, or the duration of time these atoms can change into new stable isotopes. So is it the pursuit of knowledge? Sure. We always want to enhance our understanding about geologic age and geologic time, and therefore we can calculate an approximate age of rock samples or things that have organic origins, right? Things that were alive or living. All right, in this example down below, just to review, the center portion here is the nucleus, and around here is your electron clouds. Right, your electron clouds, we have a total of 1, 2, 3, 4, 5, 6. More than likely, this is carbon. You would have 6 protons, you have 6 electrons, and 6 neutrons in the nucleus. If this is carbon-14, then we would have 6 electrons, 6 protons, and 8 neutrons. All right, in this example here, we have a graph showing the uranium versus lead percentages left over. All right, 4 out of 4 is a whole, right? That's going to be 100%. 3/4 is 75%, 1/2 is 50, 1/4 is 25%, and of course 0 is 0. As time increases, or the number of half-lives increase.
Substitute Landgraf, please go to 216. Substitute Landgraf, please go to 216.
Sorry. We see that the uranium decreases with time, and lead is going to increase over time. Indirect, direct. And please remember that at half-life 1, no matter what, you would always have the lines intersecting at the first half-life.
But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with.
Just wanted to show you that this graph here is telling you that one half-life, he said on average, 5730, or 5,730 years. All right, your reference table says 5.7 only. All right, so we're going to stick with 5.7. This is just adding a 30 to each of these, right? 30, 60, 90, and then additional 120, which gives you, instead of 22,800, now it's 22,920.
And 14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
All right, this says here the half-life of a radioactive isotope is a fixed interval, does not change. In other words, right, looking at your reference table on page 1, excuse me, on page 1 we have carbon-14 as being 5,700 years, that's fixed. Potassium-40 is 1.3 times 10 to the 9 years. It's 1.3 billion years. It's a fixed rate. Okay. All right, and then we have 4.5 times 10 to the 9 years, and that's going to be 4.5 billion years. That's a fixed rate. Last one's rubidium-87, and that's going to be Rb-87. That's 49 billion, and that's a fixed interval. So it can be used to determine the approximate age of a rock layer and fossils containing the remnant of carbon-14. All right, carbon-14 used to date once living things less than 70,000 years old. Potassium-40 used to date old rocks on the Earth's surface. Uranium-238 used to date the oldest rocks on the Earth when it formed 4.6 billions of years ago. Rubidium-87 has used to date objects older than the Earth, like meteorites. Right, this rubidium-87 has not gone through one half-life on the Earth's surface. All right, these pictures here, we have armored fish, which is your placoderm fish. We have echinoderms, crinoids, mollusks, and trilobites. All right, mollusks are like your gastropods. Almost look like a snail-like organism. Can be aquatic, can be on land. We can use carbon-14 to date some of these organisms. All right, if it's older than 70,000 years, maybe we can use some potassium-40 within it. Right, down below we have the unstable atoms such as uranium-U eventually changing into stable atoms such as lead-Pb. The original version is called a parent atom or isotope, and the new version is called a daughter atom. Parent is uranium, daughter is lead. So here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 U's, 1 half-life. We'll have 4 U's remaining and 4 changing into Pb into lead. All right, the half-life of an element is a fixed rate that cannot be altered by any known process. In other words, heat and pressure, like in this picture here, we have a lot of heat from inside the Earth. That cannot alter this fixed interval, cannot make it go faster. If we had an ice age, right, it cannot make it go slower. If we have a lot of pressure building up, like where 2 plates collide, here you have your oceanic trench, subducting plate, overriding plate. A lot of pressure building up here, it's not going to increase the half-life rate, right? It's a fixed rate for all of them, even the 4 that we have on our reference table. All right, here you have a time to climb. So what I would like for you to do is practice some of these questions. And if you want to pause the screen, you can. I would pause the screen, and then I can describe the answers to you. All right, good luck. Okay, for the first one. All right, we can see the answers here. I'll describe it to you. A fossil shell contains 25% of the original carbon-14. Approximately how many years ago was this shell part of a living organism? All right, I think you already had that in the previous class. Always try and create your graphic organizer. All right, so HL, half-life. Let's go carbon-14, nitrogen, 14, and then years. All right, this is how we get to 11,400. All right, questions asking about percentages. So at half-life 0, at time year 0, we have 100% remaining, and 0% has changed over. One half-life, 5,700 years, 50% remains, and 50% has now changed over to being a stable isotope. Half-life 2, 25% remains. That's what we need. A shell contains 25% of the original amount of carbon-14. That means 75% has changed over, and the answer here is 11,400 years. Which is basically, just to let you know, 5,700 times that by 2. That's how you get it. All right. Oh, I'm sorry. That was question number, that was the last one. Kind of going out of order here. I'm sorry. Question 1. How many half-lives of time are represented by point B along the time axis? All right, point B is here, and that's 25%. So 100% is our maximum at time 0, and half of 100 is 50. So one half-life is A, half of 50 is 25, and the second half-life should be B. Half of 25 is going to be 12 and a half, and that should be half-life 3, and that's going to be location C along the x-axis. All right, number 2. Due to radioactive decay, an igneous rock sample now contains 1/4 of the original amount of potassium-40 that's originally contained. The age in years of this rock sample is approximately. All right, so 1/4. Sorry, went out of order. All right, so an igneous rock sample now contains 1/4 of the amount of potassium-40. So 0 half-lives, 0 years have passed. All right, since we're going with quarters, right, 1/4, let's just do a fraction, 4 out of 4, which is roughly 100%. 0 out of 4, right? 0%. 0 years have passed. 1 half-life, half of 4 of the whole is 2 out of 4, or 1/2. That's 50%. That means 2/4 have also now changed over. That's also 50%. Same amount. This is potassium-40. Potassium-40 is here. It's roughly 1.3 times 10 to the 9 years. So it's 1,300,000,000 years. Or, let's expand that. It's all in scientific notation. So this is 1.3 times 10 to the 9th power. 2 half-lives. Half of 50% is 25%, and that's going to be half of 2/4 is 1/4, which is 1/4. 25%. And then you have 3/4. %. We take this number and we have to times that by 2. So you have a whole bunch of zeros. You have 3, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 3 times 2 is 6. 1 times 2 is 2. We add our commas. And this is 2.6 times 10 to the 9th. And that's our answer. Right, we want 1/4. Here is 1/4, 2 half-lives. We should have 2.6 billion, 2,600,000,000, or 2.6 times 10 to the 9th power. That's what we have here. Question 3, which 2 elements are most useful for radioactive dating of recent organic remains? Recent organic remains. Now, if it's organic, that means that it has to contain carbon. A good way to remember that it has to contain carbon is on your reference table. For example, bituminous coal, right? Plant remains, living things, carbon. All living things have carbon in it. All right, so carbon-14 into N14. This ratio is what we need. Now, when I say ratio, we're talking about this stuff. Right? 100% to 0% ratio, 50% to 50% ratio, 25% to 75% ratio, 12.5% to 87.5% ratio. We can even do wholes, right? 1 whole to none. 2/4 to 2/4. 1/4 to 3/4. 1/8 to 15/16. All right, and the last one I did with you. All right, you can pause this here, give yourself a few minutes to work on the absolute dating homework on formative.